A functioning motor has three basic settings: resting, starting, and running under a load. The running of a motor creates heat. For the most part, this heat buildup is harmless, but if the heat reaches high levels, the motor's sensitive functional components are at risk. When a motor is drawing too much current and creating excessive amounts of heat, it is called running in overload. If a motor runs in overload for any length of time, the excessive heat can damage the motor. To protect motors from running in overload, manufacturers typically protect their products with an overload relay connected to the motor starter. When an overload relay trips, it opens contacts within the control circuit, stopping the motor. The most common type of overload relay uses a melting eutectic alloy. A eutectic alloy is a specific type of metal that changes directly from a solid to a liquid at a fixed temperature. In a melting alloy overload relay, the eutectic alloy is housed in a tube along with an inner shaft cemented in place. This tube is connected to a ratchet wheel. The temperature of the alloy is controlled by a heater coil wrapped around the outside of the tube. The heater coil is directly connected to the circuitry of the motor, so when dangerous amounts of current run through the motor, the wire coil will also heat up. When the heater coil gets hot enough to melt the inner eutectic alloy, it indicates that the motor has reached a dangerous overload threshold. At the elevated temperature, the alloy will instantly turn from a solid to a liquid, allowing the inner ratchet shaft to turn freely. When the wheel turns, it releases a pawl previously engaged in one of the cogs of the ratchet wheel. This pawl is connected to a spring-loaded contact fixture, such that when the pawl trips, the contacts automatically open and stops the current flowing to the motor starter. The spring-loaded contact fixture also includes a reset button so that when the eutectic alloy cools and cements the ratchet in place, the contacts can be closed by re-engaging the pawl in a cog and compressing the spring. Another important part of motor electronics is forward and reverse circuitry. Here is an example of the circuitry for a forward and reverse three-phase motor. When the motor is running in forward, the circuitry contacts are connected in numerical sequence: L1 to T1, L2 to T2, and L3 to T3. To run the motor in reverse, then, two of the contacts must be switched. In this case, L1 is connected to T3 and L3 is connected to T1. L2 and T2 remain connected. This reversal of contacts will cause the motor to run in the opposite direction. Great care must be taken with forward and reverse circuitry, because if the forward and reverse contacts ever engage at the same time, it will cause a destructive and dangerous short circuit. In order to protect against this kind of short circuit, manufacturers employ three types of interlocking safety systems. Interlocks create a web of safety checks within a circuit to prevent both forward and reverse coils from being energized at the same time. They are represented in circuitry diagrams by a dotted line. The most basic level of interlocking systems is a mechanical interlock. A mechanical interlock is a physical lock that prevents the forward and reverse contactors from being engaged at the same time. The second level of protection is an electrical interlock. An electrical interlock works by using normally closed auxiliary contacts within the opposite circuitry, so that when the forward button is pushed, there is a check to make sure no current is running through the reverse circuitry. The same is true when the reverse button is pushed. The final level of protection is the push-button interlock. This interlocking system works by physically opening the button contact within the opposing circuit. This way, if for some reason both buttons get pushed, then no current will flow at all.